Hi everybody, welcome back to my channel on Feynman integration. Today we'll be evaluating this integral that I got off of the channel Mathematics MI. I will link to the video in the description. He invoked a special function to solve it. I'm going to be solving it using nothing but Taylor series and Feynman integration. Which, I mean, and the difference is trivial. But anyway, watch his video and watch mine and you'll see the difference. Okay, we're going to be using a lot of facts. We're going to be using this representation for the arctangent, which I won't go over. We're going to be using this representation for the natural log of 1 minus x, which I also won't go over. I will just briefly say that they both come from this. They both come from the fact that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n on the interval -1 to 1. With, I believe, 1 and not actually being included in the interval, but we get around that by just taking a limit. So yeah, where was I? Yeah, and then we're also going to be using this fact, which I showed on my channel once before. It's that the alternating sum of the reciprocals of the squares evaluates to, sorry, should be a more prominent negative sign there, negative pi squared over 12. And that's in my playlist Proofs and Tools. So we will be using this. We'll also be using the fact that the natural log of 2 is equal to the negative sum from n equals 0 to infinity of -1 to the n over n. That comes from simply making x equal to -1 in this equation right here. So that would give us natural log of 1 minus -1 is 2. So natural log 2 is equal to negative sum from n equals 0 to infinity of -1 to the n plus 1 over n plus 1. Then we add 1 to the interval and subtract 1 from all the n's inside the sum, and we arrive here. The next one is that pi over 4 is equal to the sum from n equals 0 to infinity of -1. I'm sorry, this is not n equals 0, this is n equals 1. That pi over 4 is equal to the sum from n equals 0 to infinity of -1 to the n over 2n plus 1. And that just comes from evaluating this equation at the point x equals 1. All right, so let's get started. First step, we will create a function of t that is equal to the integral from 0 to 1 of x to the t arctangent x dx. And we will note that if we take f prime at 0, we will recover I. Because if you take f prime of this, if you take the derivative with respect to t of this function right here, using the Leibniz rule, you will get the integral from 0 to 1 of x to the t natural log x arctangent x dx. Evaluating that at 0 will make the x to the t go away, just become a 1. So we'd be left with nothing but this, which is I. So I is equal to f prime at 0. Okay, so next step is we are going to rewrite this f of t using this fact right here. So f of t will now be equal to, well, let's see, we're still going to have the integral from 0 to 1. Natural log x, x to the t will not change. But then our arctangent x will become the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1 dx. And then there's not going to be any problems with convergence there, so we can use Fubini's theorem. But first, we'll take this x to the t inside the sum notation, giving us inside the sum would be x to the 2n plus 1 plus t. So I'll just write that plus t right here. And we can get rid of this x to the t. And then we will switch our sum and sigma notation, our integral and sigma notations. So this is now, this will just be the integral from 0 to 1, and then we will have the sum from n equals 0 to infinity. All right. This integral is easy to evaluate. These are constants with respect to x, so all we really need to do is take the antiderivative of x to the 2n plus 1 plus t and evaluate it at the bounds. So let's see. That would give us x to the 2n plus 2 plus t over 2n plus 2 plus t from 0 to 1. The lower bound would go away because x equals 0, and then 1. This whole thing would just become a 1. So that's literally all it is. So our f of t is now simply equal to the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 times 2n plus 2 plus t. All right. We don't want f of t for our evaluation of our integral. We want f prime of t. Well, that's very easy to take the derivative with respect to t of this thing. I'm not even going to explain it. I'm just going to jump right to it. And in fact, to save a little bit of space, I'm going to erase our original definition of f of t because we don't need it anymore. That's going to give us f prime of t is equal to the sum from n equals 0 to infinity. Let's see, we'll have negative 1 to the n still. That's going to be over 2n plus 1, and then this 1 over 2n plus 2 plus t is just this thing to the negative 1. So we get, when we evaluate that derivative, we would recover a negative sign, and it would become 2n plus 2 plus t all squared on the denominator. All right. And since we're really not even interested in f of t at all, I'm going to go ahead and erase it. Because we don't even care what f of t is. That was only a tool for finding f prime of t. All right. Well, now we kind of have it. We just need to evaluate this thing at the point t is equal to 0. So let's rewrite I. So I is now equal to negative sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 times this thing evaluated at 0, t equals 0, I'm sorry, 2n plus t, 2n plus 2 all squared. There we go, finally got that. Okay, now I'm not going to perform the partial fraction decomposition on this thing. Some people wouldn't even need to use it. You can just do some clever manipulation to find out what this is. It's going to be the sum of 3 separate fractions though. Like I said, I'm not going to perform the partial fraction decomposition because that's just a long, boring process and you guys don't really need to see that. But I have it here in the notes somewhere. Yeah. So finally, when we perform partial fraction decomposition on this and factor in the negative sign, we will get this. We will have I is equal to, okay, let's see. Negative sum from n equals 0 to infinity of -1 to the n over 2n plus 1 plus the sum from n equals 0 to infinity of -1 to the n over 2n plus 2, and then finally plus 1/4 the sum from n equals 0 to infinity of 1 over n plus 1 squared. Yeah, so that's what you get when you perform partial fraction decomposition on this fraction 1 over 2n plus 1 times 2n plus 2 all squared, and then break it up into separate sums. Okay, oh, no, this is wrong. This is -1 to the n. All right, so now we're going to break out some of our tools here to figure out what all these things actually converge to. All right, well, let's see. This is simply the negative version of this, right? That's the sum from n equals 0 to infinity of -1 to the n over 2n plus 1. So this whole thing converges to -pi over 4. -pi over 4. Now what about this one? Well, we can factor out a 1/2. To make this n plus 1. Now we almost have this alternating sum of the alternating harmonic series, I believe is what that's called. We almost have this. We just need an n on the bottom instead of an n plus 1, and we need an n equals 1 there instead of an n. So what we'll do is we will increase the index on this by 1. Now to compensate for that, we must subtract 1 from all our n's. Subtracting an n from this n right here, subtracting 1 from n here will simply have the effect of multiplying the entire thing by -1. All right, so now we have, let's see, so negative natural log 2 is equal to this. So this whole thing right here is negative natural log 2. This negative and this negative will cancel, giving us just natural log 2 over 2. So that's plus natural log 2 over 2. Okay. For this thing right here, we're going to perform a similar manipulation. We will increase the index by 1 and subtract 1 from all our n's. That will make this an n squared on the bottom. And this will become a negative. right here, we have that this is equal to negative pi squared over 12. So this will become a plus pi squared over 48. And that's it. That's the whole thing right there, and I'm going to check it really quick. Make sure that I did not make any silly mistakes. So what do we have there? Negative pi over 4 plus natural log 2 over 2 plus pi squared over 48. Yeah. That is the correct answer, and hope you enjoyed that.